Okay, so we can start. Okay, great. So, okay, um, it's a pleasure to be here. Unfortunately, I wasn't able to join in person. I had another conference, zk-SNARK last week, and many of us, unfortunately, got positive to COVID. So, that was very unfortunate. Uh, so, uh, and they just mentioned zk-SNARK, where we had also the chance to start describing what is our history, where we started, and so maybe this could be also a good way for making an introduction about the topic that I will cover today. So when I joined, let me say around 5 years ago, one of the main goal we had at that time, we were Zencash, okay?
Recording in progress.
We had as a first goal to create a system for managing the treasury, so a DAO. And one of the first challenge was to understanding where to integrate this logic. As you can imagine, and Zcash was a cryptocurrency, a running cryptocurrency. And as you can imagine, as a developer, adding all this complexity to the core of a cryptocurrency was, let me say, at least probably not the best path in terms of both security, in general, about the risks that it was provided. So I started thinking at possible ways for implementing the treasury in a way that was not affecting the core. But one of the main goals of implementing the DAO was to enable decentralization and to redistribute the funds, and in a decentralized way, obviously. But how can you really, let me say, redistribute the funds in a decentralized way without having a proper protocol with the main chain? Main chain. When I say main chain, it's the core of the cryptocurrency. So, and here it's another, let me say, the big challenge was to find a way to implement a protocol that was able to enable the interaction and the communication between these parallel applications and the core of the cryptocurrency. Okay, I thought about possible approaches, and they were, let me say, in a first possible way for addressing these was creating parallel blockchains. And then I discovered that they were called sidechains. So, this was the approach that seemed to me more suitable for this. But what I understood immediately after was that most of the protocols were or semi-centralized or not scalable. So the main focus then was to try to find a way to implement fully decentralized and scalable protocol for enabling the communication between sidechains, any kind of sidechains, and main chain. Because we understood that, okay, this would have been very powerful. The possibility to have parallel blockchains with their own logic, with their own rules, decoupled from the main chain, but able to communicate with the main chain. Okay, so this was the introduction. And so today, what we are speaking about, Zendoo, that is the protocol, Latus, that is the protocol on the sidechain side, and also, a step forward that are zk-VMs and how all these together can enable scalable and decentralized applications. Okay, so let's move on. Okay, here we are. Okay, so as I was saying, what was the need? The need was building decentralized blockchain applications that are going beyond the cryptocurrency use case. So you can imagine applications that have not only coins to be managed, but also, all their data, their rules, and let me say, a whole logic that is totally different from the cryptocurrency use case. But it's important to have a real coin, because with a real coin, you can, for example, reward all the participants of the blockchain. So, I mean, forgers or whatever, I mean, the kind of consensus you have. Or, for example, if the use case need to use a coin with an already established value, for example, let's say you want to implement a car registry sidechain, you have a way for, let me say, exchanging the ownership of a car in the sidechain, but using a coin that has an already established value. And one of the other need was not creating every time you launch a new sidechain, a new token, because I mean, this is let me say, very inconvenient, because you have to go to exchanges and so on. So able to use in the sidechain the coin, one coin, okay? But at the same time, one of the need was keeping the core, the main chain, so the Zen blockchain, totally decoupled and independent from these side chains, okay? Because otherwise, I mean, if it is somehow coupled, it's not going to be scalable, and we will see later why. Okay, as we were saying, okay, let's use sidechains, no? So these are applications that are implemented as parallel blockchains that have their own logic and data, and all sidechains interact with the main chain to transfer the coins. So you can, a user can send coins from main chain to the sidechains, then they're maybe exchange them with some logic, whatever, for example, buying the car. And then, let's say, who sold the car want to send back the coins to the main chain. And one assumption that we can use is that sidechain can track the main chain. So, and what do I mean for track? Sidechain can know the structure of the main chain, can follow the main chain blockchain, let's say, and be aware of the blocks. But the other assumption is main chain cannot track the sidechains, because otherwise main chain should know the rules of the sidechains, should know the internals of the sidechain to be able to track them. And obviously, I mean, cannot track an unbounded number of sidechains. So, and this is not going to be scalable. But remember, we want to be also scalable. Okay. Okay, we ended up to a model that is called Zendoo, but in reality, we had a first version initially that was using a penalty scheme and incentive scheme to, let me say, keeping the coupled dimension from the sidechain and implementing the protocol for exchanging the coins. But then we moved on and we built a more robust protocol that is leveraging SNARKS that we are going to see today. And so, but in any case, we defined a unique protocol that has to be used by all the sidechains to communicate with the main chain. And we called it the cross-chain transfer protocol. And as we were saying, the two main operations that this protocol defines are transferring coins from main chain to sidechains, and we call them forward transfers, and then transfer coins from sidechain to main chain, and these are called backward transfers. As you can see in the schema below, you have above main chain blocks, below sidechain blocks, and you have transfers that are happening from main chain to sidechains, and then transfer that are happening from sidechain to main chain. Okay, now let's go and see in details about what are forward transfer, what are the characteristics of forward transfers. So you can imagine a forward transfer as a transaction that is included in a main chain block. What do I mean? It's a transaction that, like any other transaction, is spending main chain coins, but as an output is specifying, for example, the destination sidechain, because you remember we can have different sidechains, the user address on that sidechain, and the amount that should be transferred. And okay, and then the main chain block that is containing the forward transfer, so this transaction, can then be referenced in the sidechain. You remember, we have this assumption that sidechain can knows the structure of the main chain, so can somehow reference main chain blocks in order to provide proof that something related to that sidechain existed. Okay, but once this transaction has been processed, is included in a block, and then let me say included in main chain, these coins, the coins that we have spent and sent to the sidechains, are not anymore available in main chain. So any node in main chain is aware that the coins are not anymore there. And these coins then can be spent in the sidechain by providing the proof of ownership. So, I mean, we can include a proof in a sidechain block that this transaction happened in main chain, and the user that has the private key associated to the user address can, let me say, provide the proof of ownership and then spending these coins inside the sidechain. So they live in the sidechain, these coins. And okay, and I was saying before, sidechains are aware of this transfer because they follow main chain. Okay, now let's see the most tricky part, because I mean, assuming sidechains follow in main chain makes things easier, but now we have the harder part because it's the we are assuming that main chain is not following sidechain. So how can we implement backward transfers? Okay, first of all, let's see how they are structured. So backward transfer are initiated in a sidechain. So you can imagine a user that is has some coins in the sidechain and want to withdraw these coins in main chain, maybe for sending them to an exchange. And so he is sending a withdrawal request. You can see it again as a transaction that is happening on the sidechain side. And these withdrawal requests are collected and periodically, okay, during what we call an epoch in the sidechain. So you have several withdrawal requests coming from different users. They are collected, and then they're put together and they're sent to main chain as backward transfers in a certificate. So the certificate is, let's say, the transaction that is containing the list of backward transfers that sidechain collected in an epoch. But how can main chain really validate a certificate if it doesn't know the details of the sidechain, if it doesn't know how any main chain node can really understand if the certificate is legitimate, if really reflects what happened on that specific sidechain? Even, I mean, because it doesn't know the sidechain rules. So how can a main chain node be aware about the validity? Obviously, you can solve this by using a trusted parties or a set of trusted parties. So signing, for example, the certificate. But I mean, you remember, our first goal was to keep the system decentralized, allowing the creation of these decentralized applications. So this doesn't work. Okay, so now we can speak about the Latus sidechain structure. So let's see how on the sidechain side, transactions are happening, how they are exchanging coins, and then how withdrawal requests are processed, and a certificate is created. So because our first goal is understanding from main chain perspective what legitimate means, okay? Okay, above you can see a list of transaction sequence that are in a block, for example. So you have a transaction one that is, this is a specific sidechain example that is a UTXO based, but I mean, this applies also to account-based sidechains. Let's say you have a transaction one that is spending a UTXO1 and creating UTXO2, and another transaction that now is spending UTXO2 and creating UTXO3. And a withdrawal request that finally spend UTXO3 and create the backward transfer that then is appended to the backward transfer certificate. Okay, as we were saying, how we can really understand if the certificate is valid. Okay, Zendoo solution is using SNARKS to provide a succinct proof of validity of backward transfer. So the certificate also includes a proof of validity of the certificate itself, of the list of backward transfers. And each sidechain, when it is declared also specifying a SNARK verification key that reflect the rules of the sidechains, of that specific sidechain. So, as you've seen previously, there were a set of transactions that were happening that were respecting some rules. And the SNARK proof that is provided to main chain ensure that the backward transfer that is included in the certificate is as respected in the whole its history, has respected all the sidechain rules. Okay, in such a way, you can have that the sidechain logic is totally decoupled from main chain, and these allow the creation of any application, because main chain doesn't know the rules of the sidechain. Main chain does just know the SNARK verification key that was associated at the time the sidechain was created, and that's enough. Okay, but now let's see here a complete interaction overview. So below you have main chain, above sidechain. So let's say in main chain you have a forward transfer, so some user that is sending some coins to the sidechain. So every node on the sidechain side now is aware about the new coins. The user can perform a custom transactions that is spending these coins or others, and then some other user can do some withdrawal request. You can see a couple there, and then at the end of the withdrawal epoch, is the way we name them, there is a certificate that is collecting altogether the backward transfers that were related to the withdrawal requests. And you can see it for all the subsequent epochs. And obviously, after the certificate is included in main chain, the backward transfer, are then not anymore on the sidechain side. They were spent on the sidechain side, and they are available on main chain. Okay, but you remember we just said that there is SNARK proof included in the certificate, but what does it mean that backward transfers are respecting the sidechain rules? How can a unique succinct proof guarantee that the backward transfer is legitimate? The whole history of the backward transfer is legitimate. Okay, on the sidechain side, we can use recursive SNARKs to create a succinct proof that proves to main chain that all the sidechain rules were respected. And now we can see how it is possible. So, looking more in details about the Latus sidechain structure, and this is one example because main chain doesn't know anything about Latus, but the Latus model describes a way for proving in a decentralized way the backward transfer. So let's assume that we keep the state of the sidechain in a Merkle tree, and we can represent the state of the sidechain at any moment with its Merkle root. And obviously this Merkle tree is containing, in this example, the set of UTXOs that are in the sidechain in that specific moment. So whenever you apply a transaction that is spending some coins and creating other coins, you are somehow modifying the state. You can see that we have a state S0 and a state S1, and that we have a transaction TX1 that is happening inside the sidechain that is spending UTXO1 and creating UTXO3. And you can see that the state S0 or the Merkle tree initially is containing UTXO1, but in state S1 it doesn't contain it anymore, but contains UTXO3. So let's see what are the conditions for validating the transaction 1 in order to generate a proof of a state transition in the sidechain. So what are the what do we have to check in the sidechain to be able to transition the state? So obviously that's the input of the transaction is existing. So the state S0 is containing UTXO1, that we have a valid signature associated with the public key of UTXO1. Obviously the input and output coins are coherent. What do I mean here? That the inputs, the amounts that we are spending are, let me say, equal to the amount that we are creating of the coins that we are creating. And also that the final state doesn't contain anymore the spent coins, but contains the newly created coins, okay? So in this case, UTXO3. So if all these conditions are verified, we have a proof, we can create a proof that there is a valid transaction that caused a valid transition of the state from Merkle root S0 to Merkle root S1. Okay, and we have a SNARK proof that says that. Okay, now you can see more generally a sequence of proofs of transactions and then the relative proofs, where you prove all the transitions. You prove from S0 to S1 with the, after having applied transaction 1, and then from S1 to S2, and so on for all the transactions. Okay, so we saw so far how we can prove state transitions that were, let me say, caused by transactions. But you remember, we have withdrawal requests also that are part of the sidechain, that are the transactions that are used by the users to withdraw coins from the sidechain to the main chain. And these are important. So withdrawal requests as regular transactions are spending existing coins in the sidechain. And instead of, let me say, adding them or the newly created coins in the new state, they are appending them to, let me say, the list of backward transfers that are going to be included in the next certificate. And for keeping track of these backward transfers, we use another Merkle tree that is just containing the backward transfers that of this epoch, okay, of the withdrawal epoch. And as you're going to see here, it's very similar approach that we're using. Okay, but let's say for what regards the backward transfer Merkle tree, at the beginning of the epoch is empty, so it's not containing any leaf, or better, all the leaves are, let me say, pre-initialized with a null, let's call it this way, leaf. And every time we process a withdrawal request, we add a corresponding entry in the tree for the backward transfer that we create. So, I mean, the conditions for let me say, generating a proof for a withdrawal request is that obviously the coins that we are spending were existing in the state. And obviously that we have the public key, the private key for signing, and that inputs, so what we are spending and the backward transfer amount are coherent. Obviously that what we spent is not anymore in the state, but also that the Merkle tree of backward transfers now contains the new backward transfer. Okay, if these conditions are verified, we can prove that we had a valid transition, that in this case a withdrawal request, that transitioned both the state Merkle tree and the backward transfer Merkle tree. So we have now a proof that proves two things: prove the new state, the transition of the state, and also the transition of the tree of backward transfer for this epoch. Okay, now we can put together these two things. We have the transaction proofs that we saw previously, and we have also the withdrawal request proof. Okay, as you can see now, we are also seeing here for the transaction proof that we also keep track of the backward transfer tree. So we have S0 to S1, for example, and E0 to E1. But here, let's say the rules for creating the proof are enforcing that E0 is equal E1. So when you are processing a transaction, we are not modifying the backward transfers for that, after having applied the transaction. We are just modifying the list of backward transfer when we are applying the withdrawal request. Okay, but remember, we want to end up with a unique proof in main chain, with a certificate with a unique proof. And here we have many proofs, each one for each transaction or each withdrawal request. So how can we create one proof? So let's say that we organize all these proofs in a sort of a Merkle tree, okay? And we are recursively merging them into a unique proof. So we use recursive proof composition in order to end up with a unique proof. Okay, here, let's see this example. Here you can see that we have the proof for transaction one, that is, let me say, transitioning the state from S0 to S1, and the backward transfer list from E0 to E1, but I mean, they are the same. And then we have also the proof for the withdrawal request that is starting from S1 to S2, and also, but then is transition E1 to E2, because now we have the backward transfer in the list of backward transfers. And now assume that we are able to create a proof that is able to verify two proofs, and please follow me. So we are able to verify two proofs given the inputs, and also we verify that the end states of the proof of transaction one are equal to the start states of the proof of withdrawal request one. So keeping these two things together and having verified the proofs, let us end up with a proof that allows us to forget about the initial proofs. So now we have a merged proof that goes from S0 to S2 and from E0 to E2. And we can forget about the initial proofs. And you can do it recursively, merging all the proofs. So you saw it from TX1 to withdrawal request and withdrawal request one. So we have a first merge proof, but you can do for all the others. And you can end up recursively with a unique proof for the whole epoch. in such a way, when you end up with a unique proof that is telling you, I mean, that there were a set of valid transaction and withdrawal requests that transition the state from S0 and to SN, and also that transition the state from of the backward transfer from E0, you remember the null tree, to EN, that is another tree of backward transfers that reflect what happened on the in the withdrawal epoch in the sidechain. So now we have a unique proof that tells us what were the backward transfers in this withdrawal epoch. So from main chain perspective, we can receive a certificate with the list of backward transfers and a SNARK proof. So main chain, what we'll do, we'll reconstruct the Merkle tree of backward transfer. It will end up with a Merkle root, and then it will be, every node will be able to verify the SNARK proof against these inputs. And so it will be able to really verify the correctness of the certificate. So main chain, without knowing the sidechain rules, have verified that all the backward transfers, so the transfer happened from sidechain to main chain, reflected the sidechain rules. Okay. Another important consideration is that even if we have a sidechain that is totally maliciously controlled, it's not possible to steal the funds, withdraw the funds without knowing the private key, because all the transfers are cryptographically proven. So, and that's important. So we are not blindly trusting a set of parties. We are cryptographically proving all the transfers, the history of all the backward transfers. Okay. Obviously, I mean, in a real scenario, you also verify the belonging of transaction to a block and so on. But I mean, these are details. The main idea behind it is this one. You are able to verify the whole history of the backward transfers in a completely decentralized way. Okay, but how you can generate the proof? That's another important topic, because previously we saw the conditions that have to be met to generate the proof, and this condition let me say has to be I mean, especially some years ago, you were obliged to write them using writing a circuit, okay, using a specific logic that enforces the logic of the sidechain. Okay, so the developer had to write, let's say, two programs, one with the logic of the specific sidechain, and the other one enforcing the logic. So, I mean, this for sure is very unfriendly for the developer. So, but what happened? What is happening? Is that now it's becoming feasible creating a proof of execution of a program that is written in a high-level language, and you heard about it, without the need of writing additional logic. So you just write your logic, and then you can end up, when you run your program with the proper input, you can end up directly with the proof of execution without having to write your own circuit. Okay, and you can do it, for example, by using these two approaches. A DSL, a domain-specific language for writing circuits, or a zero-knowledge virtual machine. Okay, let's see the DSL. I mean, with the DSL, you have a high-level programming language to write programs that can be compiled to a circuit, obtaining a proving and a verification key. And the program is run, as we were saying before, with a set of inputs to compute the witness data for the compiled circuit. And then the proving key can be used to generate the proof of correct execution for the generated within state. And then you ended up with a proof that you can use in mention for proving, for example, the correctness of the certificate. Or with a zk-VM or EVM. So in zk-VM, the programming language in reality is the assembly language. So let's say that as every VM, also zk-VM has its own instruction set and bytecode format. But obviously, usually developers use a high-level language for writing their logic, but then a compiler is used to generate the bytecode of that specific VM. And okay, for what regards zk-VM, let's say that they have a state that can be composed of several things. So you can have, for example, the state of the VM that is composed by the registers, by the memory. And every time you execute an instruction, you update the state of the VM. And what the zk-VM does. The zk-VM has a unique circuit that enforces that the state of the VM is transitioned correctly every time you are executing a specific instruction. So in such a way, the generated proof ensures the correctness of the state transition of the VM given the program and its inputs. Okay, so what's the result? That the sidechain, you can integrate zk-VM and DSLs in Zendoo plus Latus, and you can end up with a sidechain whose state is fully provable, and you don't need to write circuit for doing that. And so you end up with a sidechain, the ecosystem that is fully decentralized and able to use Zen in a totally scalable way. Okay, that's it.